At the same point, positive terminal, here is L, inductor. 225 multiply with 1.414, 318 volt. DC voltage 325. The voltage must be 318 volt, but these are slightly elevated. That time the transformer is working. When MOSFET becomes short circuit between drain to source, most of the time it provides back load on this IC. These 300 volt will enter into this IC. This resistor will damage and its driver will damage. That time we need to replace this IC as well. Assalamu alaikum wa rahmatullahi wa barakatuhu. Friends, welcome back to my channel. 715G475-P004-000-001S LCD power supply. It is used in different models of Philips and ACL TV circuits and monitors. This power supply board is in two portions. The first, SMPS and backlight inverter. We will discuss function of this power supply, how it works, how to troubleshoot it in cold testing and in live testing. If you don't have good experience in electronics, never try to repair, because here are live voltage and high DC voltage. Always take care for the safety. Before touching to the board, before working, verify DC voltage on these capacitors, and board must be removed from the power. This board is divided into two portions. The one shaded line, the second this portion. In this portion, just only two connections are provided here, and separate board is installed in the PCB using these connectors. When we inject power here, line, neutral and good earth or chassis ground, this chassis ground is connected directly to this lug and it is connected to metal body. So it is chassis ground, good earth. Line and neutral, two wires enter here. Line will reach to fuse, that is here. Then it is connected to this component and here. Two components are here. On these two terminals, here is class Y capacitor and here is class Y capacitor. It is for common mode noises. These two capacitors, C921 and C920, and here is 4 ampere to 50 volt fuse, line connected to fuse, neutral and earthing at our good earth chassis ground. One capacitor is connected here, that is class Y capacitor, between good earth and this point. Neutral will reach to this component. Here is NR901, that is this component. It is NTC thermistor, SCK105, 10 ohms NTC. In this line 10 ohm, and second line is reaching here. Here C905, between these 2 points. These 3 resistors, 1.5 mega ohms, 1.5 mega ohms, 1.5 mega. 3 resistors in series, and these 3 are connected in parallel to this capacitor. Then at this point here is inductor, dual line filter from this point to this point. So it is EMI filter. Capacitor, I will make one resistor, 3 by 1.5 mega ohms. If any abnormal noise reaches in any one line or neutral, that will be grounded from this capacitor or this capacitor. If there is high rate of strike, this capacitor will damage. It will discharge all the noise in this line, fuse will open circuit, next circuit will be protected. Sometimes this becomes short circuit and we find line voltage on the chassis when we touch to the body. If the ground is not connected, if ground is connected, that time the fuse will trip off because this capacitor will give short circuit directly. If we install fuse again and again, this fuse will damage. This NTC, its function we will discuss later on. We provided line voltage 110 volt, 220 volt, whatsoever that are reaching after this protection circuit to this point. It is reaching here. It is BD901 bridge rectifier. Between these 2 points, from here to here, we have capacitor. In these 2 points we have this inductor. In cold testing, from this point to this point, from neutral to bridge rectifier, this terminal, we will receive this 10 ohms NTC because it is just only resistive component. If you cannot find continuity, maybe it is open circuit or maybe we have disconnection in the circuit. Same way, in this side we will find continuity if fuse is good. If fuse is open circuit, we will not find continuity here. These 3 components, when differential mode noise will reach at both lines, line and neutral, these are for common mode and it is for differential mode. That time this tank circuit, capacitor, inductor, these will block that noise. It will block and it will absorb that energy, and this high value resistor will dissipate that energy. So circuit will be protected. In case there are too many strikes again and again, this fuse will open circuit. Because in this circuit, MOV is not used. If MOV is present, that will eliminate all the strikes, all high voltage strikes. Bridge rectifier AC terminal, and this is positive terminal, this is negative terminal. If you check this positive terminal, it is reaching to C9031 capacitor, then it is reaching to second capacitor C902. So positive will reach to this capacitor and this capacitor. Now if we check this negative side, it is reaching to this capacitor second side, same time it is reaching to this capacitor. So both capacitors are in parallel. It is to increase the capacitance. When we plug in, these capacitors are empty. Empty capacitor behaves like a short circuit. It will try to draw approximately 10 to 20 times higher current than the rated current of the circuit at the time of initial start. For that purpose, there is NTC, negative temperature coefficient resistance. It will block that surge current that is due to these empty capacitors. So it will control the current. When controlled current is provided to capacitors, capacitors will start to charge linearly with controlled current. Same time, its temperature will start to increase because it will dissipate power. When it will dissipate power, its resistance will decrease. That time, these capacitors are charged. At that time, its resistance will approximately negligible. Its resistance will present, but that is negligible. In some circuits, there is bypass relay that is turned on after charging these capacitors. But here, this NTC is present in the circuit. These positive voltage from here, FB901, it is a jumper, ferrite bead. This is FB901. It is just only piece of conductive wire and there is ferrite bead FB. And these voltages are reaching to this point. Here is transformer winding. primary winding. Second side is connected to this point. It is D, drain. Drain, source. Drain is connected here at the same pin, D902. This is diode. This diode is connected in this way. That is this one, D902. At this point we have one diode. After diode R903, that is connected here, and we have a capacitor here that are connected to diode cathode side. This is diode cathode side. We have one resistor, one capacitor. It is RCD, RCD snubber. When MOSFET will turn off, magnetic field stored in the core will collapse. That will produce reverse voltage on this MOSFET. That will create stress, that will create power dissipation in this device. To protect it from overvoltage stress and to discharge this magnetic field, this RCD snubber will discharge that reverse polarity voltage. It is connected between positive terminal and drain pin in parallel to transformer winding. This is negative terminal. In the negative terminal we have R919. That is this one. It is here, R919, 0.33 ohm resistor. It is connected between ground terminal and this MOSFET source pin. That is here. Now come to this section. LD7750. It is current mode SMPS controller. It is switching at 65 kHz. PWM controller. It will control the switching of this MOSFET by adjusting its duty cycle to maintain the voltage in the output side. Let's see its configuration. We checked this positive terminal. Here is 682, 6.8K resistor, then this one, then this one. Three resistors are connected in series and it is connected to pin number 8. Pin number 8, this is high voltage pin. From this terminal, 3 by 6.8K resistors. When it will receive voltage here from internal charging circuit, it will provide controlled voltage at pin number 6. Pin number 7 is not connected. At pin number 6 we have C917, one capacitor, and we have another capacitor C916. It is VCC capacitor and this is decoupling capacitor. Pin number 5, from this point, it is reaching to this jumper. This jumper is connected to 22 ohm resistor and in parallel there is a diode D904. It is connected in this direction. Cathode side is here. Normally when pulse will high, this diode will remain reverse biased. But when discharging time, it will provide easiest path and it will remove all negative spikes. 22 ohm resistor and this diode in parallel. Then it is reaching to 10 ohm resistor. Then it is reaching to gate. At the gate we have 10K resistor. It is connected between gate and ground, that is this ground. It is gate discharging resistor, 22 ohms, 10 ohms, 22 ohms. From this point where we receive voltage for this source pin, at the same pin from this terminal there is a line from jumper 903. This signal from this point, this signal is reaching to this 220 ohm resistor. Then it is connected to this capacitor. It is current feedback. How much current will flow in this MOSFET? This voltage drop will reach to this IC pin number 3 from underside of this IC at this terminal. Pin number 4 is connected to ground. Pin number 2, that is connected to this capacitor. Same time it is reaching to this jumper. Then it is reaching to this point. Here is optocoupler. This collector is reaching at this point. This is collector and this is emitter. Emitter is connected to primary ground. This capacitor ground and this point, it is reaching at this terminal, pin number 4. All these are grounded. This ground at this capacitor point, then it is reaching to this capacitor, then it is reaching here, and it is reaching to primary ground at this capacitor, at bridge rectifier, this terminal, negative terminal. Then we have pin number 1 of this IC. OTP pin is pin number 1. It is multifunction. It can be programmed for different functions, for rebooting, for reboot disabling, for temperature compensation, for shutdown. But here it is for normal operation. Pin number 1 is connected to 104 100K resistor and primary ground. In some circuits, in some models, this resistor will be not used that time. This capacitor, this resistor, this resistor, this resistor, and it is connected to capacitor positive terminal. It is to sense the line voltage. As I discussed, maybe this pin can be assigned for different operations, but in this case it is not using this function. It is using just only normal operation, that is 100K resistor. When we plug in, controlled current will reach to this capacitor. It will start charging. Same time the voltage will start to reach at this pin. It will provide charging current for these capacitors and chip biasing current. So these capacitors will start to maintain charge at this pin. Here the voltage are also building. When it will maintain initial startup threshold, that is about 15-16 volt, that time it will start switching. When it will start switching, it will create pulses here, 65 kilohertz. These pulses will reach to this pin. That time this MOSFET will turn on. It will provide current in this path. Transformer will create magnetic field. That magnetic field will be stored in the core and it will transfer voltage in other windings. How much current is flowing in this channel, that will be measured from this pin. If there is overcurrent condition, that time this IC will stop switching. It will hold the switching until the current level is decreased. Now there is another winding in this transformer, in this portion. This point that is connected to primary ground, this bridge rectifier negative terminal. So winding this end is grounded. Winding this end is connected to R470, 0.47 ohm resistor. Then it is connected to this diode. Here is VCC diode or auxiliary winding diode. Then it is reaching to this point. It is C916 VCC capacitor. I will create part of this winding, this transformer winding here. This end is connected to ground, and here is 0.47 ohm resistor, this rectifier. This resistor is to adjust VCC voltage. It will rectify the voltage. At initial startup, this IC will receive voltage from here. It will start switching. When it will start switching, this capacitor will start to decrease. If in that time, that switching time, it will not receive voltage from this winding, voltage level here will drop. This IC will go in cut-off state. In that condition, the IC will shut down for a while until the voltage will maintain again at the threshold. Let's suppose initially it was started at 16 volt. Due to any reason, we are not receiving voltage from here, so this capacitor will start to decrease, discharge. Why? Because this resistor is not providing enough current. That is just only for startup. But now when this IC started working, it needs more current. When this IC will need more current while switching, that time it will start to decrease the voltage level on this capacitor. Anytime the voltage level here will drop, then the threshold, its internal circuit will disable. If the circuit is working good and we are receiving voltage here from this side, that time it will work in smooth running. Due to any reason, if the voltage will increase at this pin, then its allowed threshold, that time this IC will go in overload protection. Voltage will drop, it will go in reboot. If voltage will exceed then allowed limit, that time it will go in overload protection. If it is working normal, there is overload due to any reason. If the pulse level here will increase than allowed threshold, that time it will skip the pulses so that any abnormal condition will be removed. Now let's see the secondary side. This winding end and this winding end. This end is reaching to this point and it is connected to jumper to this side. Here is D901, two rectifiers in one body, and this is cathode output. One winding, two rectifiers. I will make only one because two are in parallel. This secondary side ground. In parallel to this rectifier set, we have 47 ohm resistors, two resistors in parallel, then this capacitor and this capacitor, this RC snubber here. It is for its fast recovery. Then we will receive voltage at output capacitor, that is C908. Same way, this winding, this end is reaching to this rectifier here, and here is jumper, cathode output, same RC snubber is here. This is second winding. And this is 5 volt section. It is 16 volt section. In 16 volt section, here D1207, 2SD1207 base collector emitter, it is shunt regulator. And there is a zener. Here is 510 ohm resistor, and it is connected to this 102. In parallel there is a capacitor here. It is connected to emitter. So it will maintain the voltage at 16 volt. If you see this 5 volt section, this is output point, cathode point. At cathode point we have one jumper here, and it is reaching to this feedback network. We have this jumper, it is reaching to this 100 ohm resistor and 1.5k resistor. This 1.5k resistor is connected in parallel to the optocoupler. That is this one that we discussed here. This point I will say A. This point A is connected here. Here is TL431. Cathode is connected to LED, optocoupler LED. Anode is connected to ground. That is this ground from here. Cathode is connected to this capacitor that we mentioned here, C910. At the same point, positive terminal, here is L, inductor. This inductor is reaching here. Then it is reaching to this capacitor, C911. C911, this point is jumpered here and it is reaching to this side, and it is reaching to this voltage divider network. Here is 1002 10k and this resistor 9.1k. This point B is here. Between cathode to anode, this capacitor is connected between cathode pin and this 4.7k resistor and reference pin, 4k7. This is 10k, 9.1k. It is voltage divider network. It will not allow this TL431 to switch at any abnormal pulse. After that there is output fuse. That is this fuse, 4 ampere. In this model, small connector is used here, that is ground 5 volt for motherboard, for the main board. Here is dim light and enable pin, 2 signals. These are coming from microprocessor. When we will provide ground at 5 volt to the main board and we turn on the TV or the monitor, that time dim signal and enable signal, 2 signals will reach here in this board. That are these 2. And at the same time, this 16 volt power supply from here, this is ground, and these are 16 volt from this terminal. From shunt regulator, 16 volt and these 2 signals, enable and dim signal, these 4 lines are reaching in this portion. Positive 16 volt, ground and enable and dim signal. These 4 pins are connected to this PCB on these lines. That time this IC will receive this PWM signal. It is backlight driver IC. It will control the switching of this MOSFET and it will provide voltage for the backlight. In my last repair I found this capacitor bad and it was 4.7 microfarad. The original capacitor was 4.7 microfarad 100 volt. I missed it. I installed 47 microfarad and I received comment from my viewer and I am thankful for his observation. He mentioned that I installed 47 microfarad capacitor instead of 4.7. This capacitor was short circuit. It damaged this MOSFET. This damaged MOSFET was causing to pull down this 16 volt. that was causing to fluctuate the power supply. When I disconnected this MOSFET, this capacitor, the voltage built up 16 volt here. Now let's see how to test it. First we will check cold testing. We must verify voltage on these capacitors, DC voltage. No voltage, it is good. Sometimes there are 5, 6 volt, 10 volt that are safe, but for multimeter that voltage are not safe. Might be 10 volt, but when we will connect this multimeter, maybe it will damage 0 volt. That's good. In diode mode, we will connect black lead at capacitor positive terminal, and we will check with these line terminals 0.522, 0.510. We can see there is a little difference, that is due to NTC. 0.51, 0.52. Now move black lead to the negative terminal, open circuit. It is good indication. Swap the leads. Red lead at negative terminal 0.508, 0.524. So both side line terminals will show the diodes. So both side line terminals will provide diode drop voltage. That is good indication that this bridge rectifier and its components are in line. Move red lead to positive terminal, check with input terminal, it is open circuit. It's good. Now red lead at negative terminal, black lead at positive terminal of the capacitor, 0.527, one diode drop, it is good. Here open circuit, it is good indication. If you cannot find this, if you cannot find these measurements, then we need to check components in this zone before bridge rectifier. That time we will use resistance mode. AC input terminal of bridge rectifier and line input terminal, fuse at this portion. Then second side we are receiving 10 ohm resistor, that is from this NTC. In resistance mode we will connect at input terminals. We will receive in mega ohms, in 100 kilo ohms, 100, 200, 400, like that. If it is in kilo ohms, 1 kilo ohm or less than that, that time there is something wrong in the circuit. That time the input resistance is low. Both sides the resistance must be high. If this capacitor is short circuited, if there is MOV short circuited, that time we will receive in few ohms, less than 100 ohm. So that time we need to verify these components. Move to diode at VCC capacitor positive terminal, this one, and ground. We will check this diode now. This is VCC capacitor positive terminal and bridge rectifier negative terminal, 0.522. If this diode, this resistor winding are good, that time it is good. Reverse the leads. It is open circuit. That's great. If we don't find reading or we find short circuit, that time we need to check this zone. As we tested between bridge rectifier positive terminal and negative terminal, one side one diode, second side open circuit, that time we are testing varistic diode in this MOSFET. Between drain to source, this diode is reflected here. If we find short circuit here, that time we need to verify the MOSFET. Now in resistance mode, we need to check source pin and ground terminal. This time we are testing this zone. In some cases, if this resistor is open circuit, everything is good, it will not switch. So we need to verify source pin with negative terminal of the bridge rectifier or negative terminal of the capacitor. Then drain pin and positive terminal. It will give low resistance from this path. Now we tested this zone. The primary side main checks are good. Now if it is not switching, that time we will verify voltage on VCC capacitor, either it is building or not. If there is any fluctuation, we will check live voltage here at this capacitor. These must be stable. Line voltage, how much AC voltage are here? Multiply with 1.414, we will receive that value at these capacitors. Let's suppose 220 volt, multiply with 1.414, 310, 312 volt will here. These must be stable. If that are fluctuating in 310 volt range, 310, 280, 320 like that, that time the IC is in reboot mode. If we find the same voltage as applied voltage, 220 volt here, that time this capacitor is disconnected internally. That time we need to remove and test the capacitor. Sometimes circuit is working good, but we don't find output voltage properly. Let's suppose the IC is switching. We need 5 volt in the output and we are receiving 3 volt, 2 volt. In that case, this diode, this capacitor, this resistor, these are not discharging the core. We need to check these components. If IC is not switching, we will verify voltage at pin number 6, that is VCC pin. If it is good, then we need to check the switching, or we need to verify these components. MOSFET in diode mode, drain to source open circuit, second side one diode. So if this indication is in this way, we can say MOSFET is good. If it is short circuit, most of the time it is short circuit in power supply failure cases, that time that MOSFET is to be replaced. When MOSFET becomes short circuit between drain to source, most of the time it provides backload on this IC, that these 300 volt will enter into this IC. This resistor will damage and its driver will damage. That time we need to replace this IC as well. When output voltage will start to maintain in output area, it will provide voltage divider reference here. This TL431 will switch. It will drive this LED, that is optocoupler LED. It will generate a light. This light will reach to this optocoupler transistor. It will connect this ground side here to provide sync current to this IC. So this IC will adjust its duty cycle to provide output in the output side, to regulate the voltage in the output side. This winding will switch, voltage will be rectified, capacitor, inductor, then these voltage are reaching in output side. Same here, these 16 volts are provided here, rectified, and shunt regulator will regulate the voltage and we will receive 16 volt. Let's check it practically now. If you don't have good experience in electronics, never try to test it live, because we will apply line voltage and these are unisolated. Never touch in this portion or in rear side in hot area. I applied power using series lamp. That is best way in troubleshooting. First we will verify line input voltage. At input terminal AC voltage 225 volts. 225 multiply with 1.414, 318 volt. DC voltage. Verify voltage on bridge rectifier output side. If you find 318, 325 like that time the IC is working. The voltage must be 318 volt, but these are slightly elevated. That time the transformer is working. That time the back EMF is also included in this voltage. So that is reason we are receiving 325 volt. If we have same 318, most of the time the IC is not switching, the MOSFET is not switching. Now we will check voltage on VCC capacitor. That is here. 15 volt, and these are stable. If these voltages are fluctuating, that means the IC is restarting again and again, again and again. Maybe the feedback is missing, maybe RCD snubber is bad, maybe the bulk capacitors, these capacitors are not good. Now we will check voltage here in the output side. Center pin cathode, this rectifier 5.2 volt, this side rectifier 5.2 volt, this rectifier 16.3 volt, this rectifier 16.3 volt, and then we have this filter network, and we are receiving output voltage. If any one line is short circuited with ground, that time that line will not show voltage on these rectifiers. So these are the basic checkpoints for this power supply. You can use oscilloscope to test it, but for these power supplies it is best way not to use oscilloscope until we are working in advanced level. If you are working in reverse engineering or you are in designing phase, that time we can use oscilloscope. Yes, now it is safe. If you think this video is informative, if it is good, give a thumb up. If you have any question, please write in the comments. Thanks for watching. Assalamu alaikum wa rahmatullahi wa barakatuh.